Good morning. Thank you for inviting me to speak today about a similar particle, poorly soluble particle known as carbon black. And I'm a medical doctor. I'm actually at the end of the line. When you folks make regulations, I'm the one who has to explain them to patients. And I have to exercise good judgment that goes beyond the boxes we're trying to put all these studies into. And I try to exercise common sense and good judgment when I have risk assessment discussions with patients who are concerned about exposure to all sorts of materials. However, today I'm speaking primarily in my role as chair of the scientific advisory group of the International Carbon Black Association. I've been a chair of this group for about 20 years, and as you can see here, the ICBA, very much like the TDMA, is a scientific nonprofit association. It's chartered in the U.S. It was actually formed in July 1996 after a review by the International Agency for Research on Cancer in 1995. The ICBA consists of all major manufacturers in Asia, Europe, Canada, and the United States, and our mission is very straightforward. We want to make sure that people who make and use carbon black don't get sick from making and using carbon black. So our fundamental mission is to address the safety, health, and environmental issues having a common impact on member companies. Today, what I'd like to do in follow-up to Dr. Freisek, who gave you a primer on epidemiology, is I'm going to talk about the epidemiology studies of carbon black workers. Now, one of the questions that was posed earlier about TiO2, generally speaking, you do not have smoking data in mortality studies. You essentially have death certificates, and you have some exposure information. It's very uncommon on the death certificate you have smoking information. So morbidity studies may have smoking data, but generally speaking, mortality studies do not. I'd also like to give you a little glimpse, frankly, of some cellular responses to inhaled particles in lab animals in contrast to humans. Well, as we all know, studies of lab rats exposed to particles under conditions of lung overload indicated a risk of lung tumors. But why were these studies done? Does anybody know why these studies were done? Why were they done in the first place? Well, it was actually an epidemiology study of railroad workers in the late 1980s suggested a risk of lung cancer from exposure to diesel exhaust. Eric Garshik, a colleague of mine when I was at Boston University Medical Center, he did this study. I've known Eric for many years, and as a result of his work, let's take a look at this. This was published in the American Review of Respiratory Diseases in 1988. He looked at 55,000 white male railroad workers, tremendous number of deaths. That's almost 20,000 deaths. If any of you have any experience with mortality studies, you know that's a substantial number of deaths. The relative risk was 1.45. Another way of looking at the SMR, as John Freisek told you, this essentially means that the railroad workers had a 45% higher risk of lung cancer in comparison to controls. As you can see, the 95% confidence limits, the lower limit is 1.1, therefore it is statistically significant. What does statistical significance mean? Usually you have statistical significance at the 95% confidence limits. That means you have 95% assurance that these results are not due to chance. Any study has a potential for the results being due to chance. So as a result of Eric's work, he developed an hypothesis: occupational exposure to diesel exhaust results in a small but significant elevated risk for lung cancer. Where do we go from there? Well, in the early 1990s, primarily in Germany and the US, 2-year inhalation studies were conducted. The purpose was to evaluate whether diesel exhaust, which, as you know, consists of about 95% or 65% pure carbon and the rest being an organic fraction, was it the organic fraction that increased the risk of lung cancer? That, frankly, was the working hypothesis. Carbon black was chosen as an inert control because it's approximately 99% carbon. So you have a nice study, you have the diesel, which is carbon and the organic fraction, then you have carbon black, exclusively carbon. Similar studies, as we've heard many times over the past 2 days, of mice, hamsters, and guinea pigs did not indicate a risk of lung cancer. And the results in rats, over 25 years later, continue to raise questions about potential risks to humans from exposure to similar particles. In my experience, the science has been settled. Now we're trying to find what regulatory box to put the studies into. Next. Well, how do we interpret rat inhalation studies for human risk assessment? Remember, we're focused on workers and people. So how do we use rat data to make sure people don't get sick? Well, lung tumors developed, as we know, only under conditions of lung overload, a term introduced by Paul Morrow in 1988, as indicated by Gunther Oberdorster yesterday. But what is the clinical relevance? Remember, I'm a physician. I see patients. What is the clinical relevance? What does it matter? Well, it has been recognized for decades, even when I was in medical school, that certain diseases associated with chronic inflammation, including pulmonary fibrosis, ulcerative colitis, have a higher rate of cancer. Why? Increased cell turnover. If you're making more widgets, you have a greater chance of making an abnormal widget. What is cancer? Cancer is nothing more than an abnormal cell that's growing beyond normal control measures. So if you make a lot of cells, make a lot of product, you're going to increase the chance of making a rogue cell. Next slide. I couldn't resist putting this paper in, which was published in Science in January 2015. And it's fundamentally saying the same thing that I just said, that some tissue types give rise to human cancers millions of times more often than other tissue types. We're all familiar with colon cancer. Has anybody in this room ever heard of small intestine cancer? No. The lifetime risk of cancer from many different organs has a correlation coefficient of 0.81 with the total number of divisions of the normal self-renewing cells, maintaining that tissue's homeostasis. In plain English, the more cells turn over, the greater the risk of lung cancer. Well, let's take a look at human studies in cancer risk. How do we evaluate the rat studies? Well, John Friesick gave you a good primer on epidemiology and an excellent summary of what's been done in TiO2. My challenge today is to tell you a little bit about what's been done with carbon black. Now, fundamentally, it's cohort mortality studies, which is groups of workers are evaluated for risk of death in comparison to some reference population. A key point in epidemiology is determining the proper reference population to which you should compare your study group. Now, there have been carbon black studies in Germany, UK, and the US. One particular study I'd like to highlight is a US study that was just published within the last year and a half. And our objective, much like the TiO2, was to evaluate lung cancer and respiratory disease mortality associations with cumulative inhalable carbon black exposure among 6634 US 8 carbon black workers. Now, in this analysis was using standardized mortality ratios and Cox regression analyses. Now, what was of particular value to us in this study, which in my view makes it a significant study, is for every person in the cohort, we had a cumulative exposure measurement. You probably know that if one way of evaluating cigarette smoking history, if you smoke a pack a day for 20 years, in clinical medicine, we call that 20 pack years. If you're exposed to 1 milligram per cubic meter of TiO2 or 10 parts per million of benzene or whatever it may be, 1 milligram per cubic meter times 20 years would be a cumulative exposure measurement of 1 milligram per cubic meter, or 20 milligram per cubic meter years. A milligram per cubic meter times 20 years. For every person in this cohort, we had a cumulative exposure metric, because we had job classifications. We also had actual exposure data that were published back to 1979, reflecting over 37 years of actual real data. So as we all know in occupational medicine, what we're trying to do is evaluate whether there's a link between exposure and some designated health effect. Is it benzene causing leukemia? Is it asbestos causing lung cancer? Is it carbon black causing morbidity? The fundamental issue is two major variables, whether there's a link between exposure and some designated health endpoint. Well, I'm going to go through these fairly carefully because we can go into as much detail as you'd like, but we looked at lung cancer mortality in the total cohort. As you can see, the SMR, remember that's the rate of disease in the study population divided by the rate of disease in the reference population. So an SMR of 0.77 means that carbon black workers had 77% of the risk of the general population. As you can see, the confidence limits are less than 1 on both the bottom and the top, which means that there was a statistically significant deficit in lung cancer. The hourly male workers had a little bit higher SMR of 0.87, but nonetheless still less than 1, which means that the carbon black workers had less lung cancer than the general population. There was no exposure response association with time-dependent cumulative inhalable carbon black. The exposure, the dose response, as you all, I'm talking to toxicologists, this is something Paracelsus told us 500 years ago. It's the dose that makes the poison. If you don't have a dose-response relationship in your analysis, you don't have causality. So there was no exposure-response association with time-dependent cumulative inhalable carbon black. And we also looked at the hazard ratio, another way of looking at whether or not there is a risk from exposure. And we looked at hazard ratio based on cumulative exposure. As you can see, even in the highest exposure, 100 milligram per cubic meter years, which means that somebody was exposed to 2.5 milligrams per cubic meter for 40 years, 40-year work line, and there was still no statistically significant excess in lung cancer. So the authors concluded that quantitative carbon black exposure estimates were not related to lung cancer or non-malignant respiratory disease mortality. Now, a point that I want to mention that we in our scientific advisory group, we will help the investigators. This particular study was not done by us, but was done by an external group, and we try to do that as much as we can. Our scientific advisory group, as the middle initial stands for, we advise. We advise industry, and when necessary, we will work with outside organizations to do high-quality science. Now, there's two other studies I wanted to get into. One of which the key author, Tom Sorohan, is right here, who could speak in more detail about this than I can. But this is a cohort of British carbon black workers. There are about 1,147 workers in this cohort. And Tom and his group, since 1985, up until we did this cardiac study about 2 years ago, have been continually analyzing death certificates that were provided to Dr. Sorohan over this period of time. So this particular cohort has been periodically evaluated as new information becomes available, as new death certificates are provided. Now, in this case, the lung cancer SMR was 1.73, which on the face of it suggests that there was a 73% excess in lung cancer in the cohort, the carbon black workers, in comparison to the general population. It was also statistically significant, as you see there, with the 95% confidence limits. So that's the first blush. Any epidemiologist will know that that's the first cut, and now you have to understand why. One of the first things you do is to see whether there's a dose-response relationship. Did workers who had the highest exposure have the highest risk, just as Paracelsus told everybody 500 years ago? There was no trend, however, among cumulative exposure. And this was also lagged for 20 years. As many of you may know, the National Cancer Institute many years ago has proposed doing about a 20-year lag, and that's to address the concept of latency. I mean, you can smoke five packs of cigarettes a day for the next five years when you're in your 20s, you still won't get lung cancer at that point. You may have to wait 20 or 30 years. So latency is the interval between first exposure to a hazard and the development of a disease. For solid tumors like lung cancer, the latencies are usually about 20. Some unusual cancers like mesothelioma, excuse me, the lung cancers can be, the latency can be as up as 30. For blood-forming organs, cancers of, for example, like leukemia, the latency can be as little as 5 years. So Tom and his group did lag the analysis for up to 20 years, and there was still no elevation. So what was peculiar about this study, and perhaps we can talk about it if you're interested in the discussion section, but the elevated lung cancer SMRs were only elevated at 2 plants. The SMRs at the other 3 plants were unexceptional. And as I said, Dr. Sorohan is here to amplify any of these. There was these points. There was also a German mortality study that was done in one particular plant in Karlsruhe, which is near Cologne, Germany. This has been evaluated in a number of different occasions and led to some very interesting scientific studies that I don't have too much time to go into in great detail here. But the initial evaluation, and this is where's John Freisig? John, this is a classic teaching case. I often use this case when I teach, where the initial SMR was 2.18 with confidence limits of 1.6 to 2.8, which suggests a twofold risk of lung cancer. Well, this is the importance of reference equations and your reference group. When we initially compared this SMR to national German rates in all the German states, the SMR was 2.18. Well, little do we realize that North Rhine-Westphalia, which is the state in which the plant is situated, has the highest smoking prevalence in all of Germany. So what do you think is going to happen if you compare it to a population where there's low lung cancer risk in comparison to a state where there's a high lung cancer risk. And remember, your study group is coming from North Rhine-Westphalia, so you want to compare apples to apples, basically. So you want to compare your study group to a reference population that matches the study group in every conceivable way aside from the exposure of interest. This is fundamental epidemiology. So when we looked at used North Rhine-Westphalia as the reference group, the SMR went down almost 20% because of the high rate of smoking and high rate of lung cancer as it was in North Rhine-Westphalia. As I said, North Rhine-Westphalia had a higher background rate of lung cancer due to a higher prevalence of cigarette smokers in the general population. Now, to reiterate the question that was posed to Dr. Freisig, mortality studies rarely, if ever, have smoking data. So it's almost impossible to separate out the smokers from the non-smokers, clearly, unless you have that data. But remember, you're looking at two fundamental variables. You're looking at the death certificate, which, in my experience in the US, rarely, if ever, includes smoking information. You would have to do an additional effort, like in a nested case control study or further epidemiological analyses, to find out whether there was a smoking link. Once again, there was no positive trends with carbon black exposure. In other words, there was no link. In fact, the highest exposures had the lowest risk. We also did further analyses. We took, Peter Morfeld and I, we segmented out the lung cancer cases and did what's called a nested case control study. That means where you have your cohort, you take out the lung cancer cases, and then you do a case control analysis. Case control studies are very effective for rare diseases. They're also very effective for looking at specific elements that may increase the risk of exposure. And when Peter and I did these further analyses, we found that smoking and prior exposures, most notably lung cancer, were really what the known carcinogens that increased the risk. I didn't realize this. One of the fascinating aspects of epidemiology is what you learn along the way. I didn't realize that the Russians kept German prisoners after World War II in prison till 1953. I also didn't realize, and there was prisoner of war records that we were able to find out job histories of German employees prior to joining the plant in Karlsruhe. Because initially when this analysis was done, we found out that the people who were hired at later ages, those hired at age 45 and above, had the highest risk of lung cancer. Now, you don't have to be an epidemiologist to realize, well, gee, if they were hired over age 45, what did they do from 20 to 45? And it's through Peter's efforts we found out that the Russians sent a lot of the Germans, prisoners of war, to uranium mines in Silesia that Peter was able to dig out of old prisoner of war records to help explain why this excess. So we could not find the link with lung cancer, but we did find the link with smoking and previous exposures, primarily to crystalline silica. Well, we've all heard about IARC, the International Agency for Research on Cancer, which is part of the World Health Organization. In 1995, carbon black was evaluated, and then also in 2005, or 2006, I think it was February of 2006, carbon black, TiO2, and talc were evaluated together. And you know by now how the IARC process works, where IARC will bring together various experts who may have published in the field or are knowledgeable about the field. And they put together this working group that critically reviews the literature on the topic of interest. And in this case, it was carbon black, titanium dioxide, and talc. And IARC noted in their review that exposures of workers at carbon black production sites are the most relevant group for an evaluation of potential cancer risk. What does that mean? It means fundamentally that if the higher exposures don't have a risk, you can guarantee that the lower exposures don't have a risk. And IARC, and we all know that the highest exposure to carbon black occurs in manufacturing, not use. In fact, I find this often very helpful when I'm asked about environmental risks. And one of the first things I do when trying to address environmental risks of exposure to a potential hazard is look at the occupational studies, because the occupational studies, with exceedingly rare examples, always have higher exposures. And if the higher exposures have no risk, you can count on the lower exposures. Now, granted, there are exceedingly rare examples where dose response doesn't come into play. Things like some sensitizers, like some of the amines in particular, and bizarre, I shouldn't say bizarre, but unusual substances like cobalt and beryllium, where the risk is mediated through genetic pathways. But 99% of the time, it's the dose that makes the poison. And I'm speaking to the proverbial choir here. In 2006, IARC noted also that the human evidence for carcinogenicity was inadequate. As David indicated, this is a synonym for no risk. But IARC rarely will come out and say there's no risk. They usually say inadequate. And IARC affirmed the 2B classification. Well, what does this have to do with rats and lung cancer under conditions of lung overload? First of all, this is not new news. And I see some of the people here, in 1995, when I was director of environmental medicine at MIT, we received a grant to have a workshop to try to address these lung overload studies that were conducted in the early 1990s. We published it as a special supplement in Inhalation Toxicology in 1996. Subsequent, through a leadership, again, of David Warheit, through the International Life Science Institute in Washington, a workshop was convened of epidemiologists, toxicologists, pathologists, physicians, to look at the lung overload studies in terms of whether they really indicated a risk to people. And these older results are now under reevaluation, frankly, in my view, for regulatory purposes, as to find out which box we're going to put these results into. Frankly, rather than boxes, I think we should resort to good old common sense, but be that as it may, we can talk about that later. What was the workshop consensus report? It was published in Inhalation Toxicology that poorly soluble particles, perhaps carbon black, coal, diesel soot, talc, titanium dioxide, elicit tumors in rats when deposition overwhelms the clearance mechanisms of the lung, resulting in a condition of lung overload. I apologize for telling you this. You've heard it 5 or 6 times already, but some points are worth reiteration. At the ELC workshop, we said since the apparent responsiveness of the rat modeled overload is dependent on coexistent chronic active inflammation and cell proliferation, at lower lung doses where chronic active inflammation and cell proliferation are not present, no lung cancer hazard is anticipated. This is a very important concept. If you prevent inflammation, you prevent cancer. More and more in clinical medicine, we're recognizing the importance of inflammation as a mechanism of disease. Inflammation is being recognized, frankly, as a cause of coronary artery disease. It's recognized as a cause of a lot of different lung diseases. And it's really inflammation that seems to increase the risk for many different illnesses, including cancer. Let me briefly talk about bronchoalveolar lavage. We haven't talked about this at the conference, but I think it's germane to evaluating risk to humans based on animal studies. Bronchoalveolar lavage is widely used in clinical medicine. I practice in the pulmonary division at the Brigham and Women's Hospital in Boston. Bronchoalveolar lavage is a routine diagnostic studies. In plain English, you put a tube, a bronchoscope into the lungs, and you instill saline, and then you extract the cells that come out. You can look for neutrophils, you can look for lymphocytes, you can look for malignant cells, and so forth. This is a very common procedure in clinical medicine worldwide. Now, let me just give you one example. I know Dr. May Young will be talking about co-workers momentarily. But there are all sorts of examples where bronchoalveolar lavage has been used in the context of occupational medicine evaluation. Minors with co-workers pneumoconiosis, for example, had no increase in neutrophils in asymptomatic minors in comparison to simple pneumoconiosis. If you remember from some of Gunther's discussions yesterday about rat studies, the rats seem to have an exaggerated neutrophilic response to inhaled particles, exaggerated vis-a-vis mice, hamsters, guinea pigs, humans, and primates. For some reason, the rats are killing an ant with a sledgehammer, metaphorically. So using BAL examples, we haven't been able to find that the co-workers had higher rates. And frankly, the prominent role given to BALF, polynuclear, basically neutrophils, in relation to particle lung exposure does not correspond to humans. What's happening in rats is not happening in humans upon exposure to particles, whether it's TiO2, coal, carbon black, et cetera. Similar findings do not appear to occur in high dust exposed workers. Let me take, this slide may seem pretty busy, but it's a way of amplifying the obvious. If you look on the left-hand first column there, you see there are 5 key parameters: likelihood for overload, neutrophilic inflammation, epithelial and interstitial proliferation, septal fibrosis, and location of the particles. You can see that the rats have a higher response in all those 5 parameters, and I'm not the first one to point out that Gunter and a number of others pointed this out yesterday, that the location of the particles in the rats is in the alveolar region. In humans, it's in the interstitium. If you think of the lungs as nothing more than tubes and tissue, the air goes down the tubes, it goes into the alveoli where gas exchange occurs. The interstitium basically is the parenchyma. That's the tissue that supports the airways. And when the particles are in the interstitium, it has a pronounced different effect than when the particles are in the alveoli. So you can see the mouse has a likelihood for overload. The hamster doesn't. The hamster has rapid clearance, as you know. The likelihood for overload in humans, I think, is, questionable may be kind. I would probably use a different word, calling remote. But be that as it may, it's clearly different. There's low neutrophilic inflammation in primates and humans in comparison to rats. There's really no interstitial proliferation in the humans in comparison to rats. It's dubious about whether there's septal fibrosis. And as I indicated earlier, the location in the humans is clearly different than in the rats. So what does all this mean? And this is my view. The greater sensitivity, in my view, we could debate the proper term to use, whether it's sensitivity or responsiveness, but the greater sensitivity of the rat lung regarding oxidative stress and epithelial cell responses is most likely due to a more pro-inflammatory environment compared to other experimental species. You've heard earlier in this conference, and I think it's worth repeating, that essentially chronic inflammation generates reactive oxygen species, which have been shown, frankly, by Kevin Driscoll about 20 years ago to have secondary genotoxic effects. Again, not new news. This is news we knew about 20 years ago. And the inflammatory cells and activated macrophages can release reactive oxygen species and other inflammatory mediators that can induce DNA damage by a secondary mechanism. So, summary. Epidemiology studies of upwards of 9,000 workers in the carbon black industry, not quite as many as John pointed out with 25,000 TiO2 workers, but nonetheless we looked at Germany, UK, and the US. They do not provide scientific support for risk of lung cancer. So what does that have to do with rat studies, lung tumors, and TiO2? I've sat through these presentations, as all of you have, the last couple of days, and a couple of points I'd like to make. Yesterday, we heard discussions from pathologists about, are these tumors really cancer? Are they keratin cysts? Are they really lung cancer? I'm surprised at this stage of the game we haven't worked that out, but be that as it may, we're also dealing with extraordinary exposure levels that are inconceivable in humans. Contrast 250 milligrams per cubic meter where TiO2 responses were observed with recent air pollution measurements in a major Asian city. I didn't want to really pick on Delhi, but if you've read the newspaper, you can see that Delhi has 900 micrograms. That's 0.9 milligrams per cubic meter. Can you imagine 250 milligrams per cubic meter? Just think about that. That's almost 300 times what you see in Delhi. You wouldn't be able to see. I learned of a carbon black study that was done in the 50s by Carl Now, where monkeys were exposed to 90 milligrams per cubic meter of carbon black. One could not see. I can't imagine 250 milligrams per cubic meter. It's inconceivable that a worker could be exposed to those levels. And at least as I see it, I know we're doing rat studies and there was questions posed, what would be a better animal model to use? That's really not my area of expertise, so I don't know the answer any better than other people. But I'm looking at this as really, a rat seems to me to be a poor physiological model for assessing inhalation risks of particles to humans. I don't see its value in risk assessment for the particular study. So in conclusion, I'd like to say that the rat inhalation studies in which exposure to carbon black was substantially higher than production and use based on decades of worker exposure. We have 35 years of measurable exposure data that have been published in the peer-reviewed literature. In my view, these rat inhalation studies are simply not appropriate for evaluating risk to humans. Thank you very much.
I have a question about the first part of your presentation. You mentioned the diesel exhaust gases and a higher rate of cancer there. So when we look at the composition, we see carbon, we see NOx radicals, we see CO, CO2, and hydrocarbons. So what do you think is responsible for the higher cancer evidence?
The particle. I mean, the working hypothesis in studies that Uwe Heinrich and Joe Morterly did in the early 90s, were the hypothesis was it the particle, the carbon core, or the organic fraction. And I went over this pretty quickly, but what happened is the carbon black exposed, the controls got lung cancer the same way the diesel exhaust exposures. Just as we learned later with TiO2, iron oxide, talc, almost any particle, even if it may be considered inert, if exposed to a rat at high enough exposures so that lung overload occurs. And basically lung overload in simple terms is more gets in than gets out. And more gets in than gets out, it stimulates an inflammatory process. So I don't think it was the particle per se that caused the increased risk of lung cancer, but it was really the inflammatory process.
Okay, I think we all agree that it's chronic inflammation which triggers the possible carcinogenic event. But our problem is whenever we try to set an occupation exposure limit, how to identify chronic inflammation in humans.
Well, there's a couple ways of doing it. One is, you have mortality studies and morbidity studies. Morbidity studies are one way of looking at the question you posed as to what the safe exposure limit be. For example, we've done that actually with a carbon black morbidity study where we had cumulative exposure measurements, and the endpoints we had were chronic bronchitis and pulmonary function testing. Now, you make an excellent point, because one of the projects, I have a grant at the moment to try to look at whether there is a way, they actually, when you monitor asthma, you can have this external breath condensate where you look at nitric acid, not nitric oxide. And we have a grant to do to see whether you have a portable device to look for inflammatory mediators such as interleukins and so forth and TNF alpha. That question is unanswered yet. So for setting up an exposure limit, my recommendation would be to use morbidity studies. Mortality studies, of course, you're looking at death certificates and people who have died, whereas morbidity studies, you have an active workforce. I agree it's not ideal when you use symptoms and lung function, because lung function, the current state of affairs is not as sensitive as other markers, but it's basically what we have.
Okay. More questions, comments for Dr. McCunney? That's not the case at this, yes.
But short-term exposure studies like Salvi and so on, there are a lot of studies available with particle, diesel suit and whatsoever. But these are only 2 to 3 hours exposure.
Correct.
And they see something in the BAL, like interleucin or myeloperoxidase activity increase. Is this an indicator for chronic inflammation?
Well, of course, you can't say it's chronic because it's only a short-term exposure. But then the question is whether the inflammation will clear once the exposure ceases. The direct answer to your question is we don't know.